So today we are going to see some applications regarding all the things that we have talked about and then try to see how those apply to some other examples in addition to the examples that we treated before now. All right. Here, the question we have for this example is this. You can see we have a circuit here. We have the AC source. We have the AC voltage source. We have a resistor here, and then we have a capacitor here. So we have the current passing through this capacitor. We have the current passing through the resistor here. So the resistance of this resistor is one mega ohm, and then the capacitance of this capacitor is 20 microfarad, as you can see here. And you can see the voltage of the volt from the AC source here is 100 sine 2 pi t volts. All right. So the question says find the current through the resistor and the capacitor. How do we find current through the resistor and the capacitor? We're going to make use of our Ohm's law. We do know that from Ohm's law, our current is equal to voltage divided by the resistance. Our voltage is given as 100 sine 2 pi t. That's our voltage. So divided by the resistance. So the resistance is 1 million, right? One resistance is 1 mega ohm. So that is like 1 million. So these two zeros will deal with these two zeros, and what we are going to have left is 10,000. 10,000 is the same thing as 10 raised to power 4. If it goes up, it becomes 10 raised to power minus 4. That is how we got this current, the current flowing through. That is how we got this current 2 amperes flowing through the resistor. All right, so this is our IR. Also, we are expected to find the current flowing through the capacitor. So we do know that the current flowing through a capacitor is IC equal to C divided T from our previous studies. So we know our C to be 20 microfarad. Micro means 10 raised to power minus 6. So you have 20 times 10 raised to power minus 6. This is C. Divided T will be obtained by, since we know our V, our V is 100 sine 2 pi T. Divided T will then be differentiating, finding the derivative of 100 sine 2 pi t. The derivative of 100 sine 2 pi t will give us, first of all, if you differentiate 2 pi t, it gives you 2 pi. 2 pi multiplied by this 100 will give you 200 pi. And then if you differentiate sine, you have cos. So you have 200 pi cos 2 pi t. That is the derivative of 100 sine 2 pi t. Now, this is basic differentiation, so I don't think I'm supposed to teach you how to differentiate now. You are way past that level, and I think you all know how to do that. So we'll just move on. So if you have this gives us the current IC that we are looking for. So automatically we obtain our IC to be equal to 4 pi 10 raised to the power minus 3 equals 2 pi t when we expand this bracket. Also, we were asked to find the energy stored in the capacitor as a function of time. And we do know how to find our energy from the previous class that we had. We know that our energy or work done will be equal to half CV squared, where C is the capacitance of a capacitor and V is the voltage. So our capacitance is 20 microfarad. So you have your 20 micro here. Our voltage is 100 sine 2 pi t. So to square that, we have 100 sine 2 pi t squared. That gives us 100 squared sine squared 2 pi t. And then this half represents, this 2 here represents this half that we have. If you expand and divide and do all the necessary mathematical manipulations here, what you will find here is 0.1 sine squared 2 pi t joules as the energy stored in the capacitor as a function of time. All right. The next question says find the energy dissipated in the resistor as a function of time. Energy dissipated by the resistor as a function of time. So the energy dissipated will be given as follows. You know that energy from the previous calculations, from the previous discussions we had, we know that energy is equal to integral of power. Energy is always equal to power times time. So you have integral of power dt here. So you have power times time automatically. Energy is equal to integral of power times time from 0 to t. Okay, so we do know that
power is equal to V squared over R, according to Ohm's law and some other discussions we've had in the previous sessions. Our voltage is V, so we have V squared over R for power. Our V is 100 sine 2 pi t at the top here. 100 is something as 10 raised to power 2. So 100 sine 2 pi t squared will be 10 squared raised to power 2 sine squared 2 pi t. And that gives us 10 raised to power 4 sine squared 2 pi t divided by R. We do know also that our R is 10 raised to power 6. That is 1 mega ohms that we have in the circuit here. So 10 raised to power 4 divided by 10 raised to power 6 sine squared 2 pi t multiplied by sine squared 2 pi t is what we're going to have as V squared over R. If we have 10 raised to power 4 divided by 10 raised to power 6, that gives us 10 raised to power minus 2. That's what we're going to have left. Then multiplied by sine squared 2 pi t dt. All you need to do is just to integrate this function, this expression here, using your understanding of integration. And when you do that, you will arrive at 10 raised to power minus 2 over 2 t minus sine 4 pi t divided by 4 pi joules. That's what you're going to obtain. So while integrating, you're going to use the knowledge of trigonometric functions to convert sine squared 2 pi t to 1 minus cos 4 pi t divided by 2. You're going to have that, and that division by 2 is what comes right under here as 2. And then this 10 raised to power minus 2 is what is still right above here, and then you can just go ahead and you can then just go ahead and integrate and obtain this value. So just try to brush up your knowledge of integration and your knowledge of trigonometric functions. That's all you need to apply here, and then you get your energy dissipated in the resistor as a function of time.
Let's move on. So we're talking about elements of AC circuits. We've talked about a capacitor. Now we want to talk about the inductor. Okay, inductance is a winding or coil of wire around a core. Inductance is a winding or coil of wire around a core. All right. So what you can see here, this is a core, right? It's usually, in this particular shape, this is a core, as you can see, and then these are the coils around the core. These are the windings of coil around the core. Core may be either insulator or a ferromagnetic material. All right. So the symbol for inductor is usually given as a winding like this. You can see this is a winding, and then it has two terminals. So it's a two-terminal element that is called just like this. Okay, and then we have another core here. There's a type of core here. This is just the simple basic kind of core that we know, and then you can see the coil around it. So there is another kind of core called the toroidal core. The toroidal core is like a donut shaped core. All right, it's like a donut shaped core, and that is what we have here. And then you can see the toroidal coil around the toroidal core here. So these are different types of cores. There are other types of cores that we could look at. Let's quickly check those out, and then we can go on. Here you can see we have the ferrite core, toroidal core. All right, we have the ferrite core, toroidal core. Toroidal, you can see it's like a donut shape. All right, so and then it's a ferrite core inductor has a toroidal ferrite core inside. So that's what makes it different from the original toroidal core. All right, so what you can see here, this is a ferrite core. It's kind of a magnetic material or a ceramic, material. This is it here, and then you can see the toroidal coil, wound round it, basically. So it just gives you an idea of this type of core. There should be one or two more types of core we have left. Let's just check them out, and then we can go ahead. We have the air core inductors. This is the fourth one we are talking about right now. We have the air core inductors. It has no core inside at all. Okay, you can see the configuration. There is no core inside at all. So you just have your windings. Can you see the windings here? You just have the windings, and then they're just connected to a pole. There is no core inside at all. All right, so this is an example. This is what it looks like when we say we have air core inductor. So there are some basic details about inductors that we should check out together, and I think we will do that now. An inductor is a two-terminal device. Pay attention to two-terminal device. Two-terminal device will mean we have the positive and the negative terminal up and down. That consists of a coiled conductive wire. Okay, so this is the coiled conductive wire wound around the core. Current flowing through an inductor produces magnetic flux. So this is magnetic flux. This is important. Current flowing through this inductor produces magnetic flux. So if the coil that makes up the inductor contains n turns, that's the number of times the coil is turned around the core. The total flux linked by n turns of the coil is given as, so this is a flux linkage. So you can see how many symbols have we talked about now. We've talked about a flux linkage. This is lambda. We've talked about a magnetic flux. This looks like a file. We have talked about n, which is the number of turns. So pay attention to that. So the flux linkage will be given as number of turns multiplied by the magnetic flux. Number of turns multiplied by the magnetic flux. And you can see we have the unit of the flux linkage as Weber. The flux linkage is what you can see here. That can you see here the flux linkage, number of turns multiplied by the magnetic flux. That is what we have here in this field. There is a field here. There is a field already produced or generated here around this particular coil. So the magnitude of the magnetic flux and the coil current are related by this expression. So you can see we have the magnetic flux here will be given as P multiplied by number of turns multiplied by the current, where our P is supposed to be permeability. P represents permeability or permeance of space occupied by the flux. Okay, permeance of space occupied by the flux, or you can call it permeability. N is the number of turns on the coil, and then P is the permeance of space occupied by the flux. Permeance is a magnetic property of the space. Okay, so you can just pay attention, take note of that. Now, the law of electromagnetic induction states that the induced voltage is equal to the time rate of the change of the total magnetic flux. The induced voltage, okay, so around the magnetic coil, there would always be a voltage induced when there is magnetic flux. There will always be a voltage induced around the coil when there is magnetic flux. So the voltage induced is equal to the time rate of change of the total magnetic flux. This is the flux linkage. All right. So time rate of this is going to give us velocity. Voltage will be equal to d lambda dt, derivative of lambda with respect to time, because we're talking about time rate. So, and we know our lambda is equal to n multiplied by the magnetic flux. Okay, so we now have d, or you replace this lambda with n and phi, so you have dn phi dt. So now our n here is a constant, number of turns is a constant, so that can just go out. So you have n d phi dt. All right, we do know that our phi is also equal to pni from what we have defined right up here. So you see that you can just replace this phi with pni. So you have nd pni dt. Also, these pn here are constant, so you can take them out. They are not variables. Okay, so you are left with n squared p di dt, where p is our permeance of space, n is the number of turns, and then you have the I dt. N squared p is usually equal to our inductance. L is usually equal to n squared p, where L is our inductance. Okay, so in this case, you can just say that our B will be equal to L di dt, and this represents the voltage, and you can find the voltage induced in the inductor. This is very, very important because we'll be dealing with that in a lot of calculations. Voltage induced in the inductor. So this is how we keep this somewhere. Also, an important expression to note is that our lambda is equal to Li. Lambda is equal to Li. This is very important. So you can sometimes say our current I is equal to lambda over the inductance. In many cases, whenever we want to find the current I, you can say it is equal to lambda over inductance. Okay, so that is why this formula is also very important. So lambda equal to Li for a linear inductor. So keep this expression to somewhere. The unit of inductor is usually Henry or Weber per ampere because lambda is Weber, all right? And then our current is the unit is A. So if you rewrite it, our L also can be equal to lambda over I. If you rewrite it, it's going to be lambda over I. So this can be Weber per ampere as the unit of the inductance, Weber per ampere, or it can simply be Henry. In today's world, generally the acceptable unit of the inductance is Henry. That is what we're using most of the time in our calculation. Sometimes when you're doing Weber per ampere, it simply means the same thing as Henry. So pay attention to those two. So we want to talk about the current voltage relation or characteristics or terminal law for an inductor. The laws of basic terminals for inductor. So we'll be looking at the current voltage characteristics. Current voltage characteristics. The voltage across an inductor is proportional to the rate of change of current. So you can say we have V equal to L di dt. This is the expression we just proved in the previous slide. V equal to L di dt, where V of t is the voltage across the inductor as a function of time. I of t is the current flowing through the inductor as a function of time. L is the inductance measured in Henry. Of course, voltage is measured in volts and current is measured in amperes. If you want to represent your inductor in a circuit, this is how you do that. You can see we have our voltage source here, V of t. We have the current flowing, I of t, and then the current flowing through the inductor, which is given here, which is our L. What you will find out here is that most of the time current flows into the inductor from the positive side. Please note this somewhere. Most of the time, or if not all of the time, the current flows in through the positive end of the inductor most of the time. All right, so pay attention to that. So let's just demystify some important details, some of the things we just talked about. Terminal law for an inductor, V equal to L di dt. You know this already, so we won't stress this much. You already know these already. We have two terminals for, this is an inductor, L. We have our two terminals here, positive and negative is the current, IL passing through the inductor. We're familiar with this already. So from V equal to L di dt, if you decide to find current, you can find current from this expression. All you need to do is just try to make current the subject of the formula and then you integrate. Make the I subject and then you integrate. When you do that, you cross multiply, you will have V dt 1 over L V dt equal to di. Okay, your di will be equal to 1 over L V dt. All right, so your I therefore will then be the integral of this. So you have integral of 1 over L V dt, or V of t dt. All right, and then from initial time to final time, you can see you have that here, then plus I of t naught. Okay, I of t naught would be the current flowing in initial current flowing to the inductor is going to be I of t naught. Okay, the initial current flowing to the inductor is going to be I of t naught. All right, so and that is going to be from t naught to infinity. Okay, so if you can convert, but if you want to eliminate this I of t naught, that means you can say that your limit will change to minus infinity to t, and then you just have V of t dt. Okay, so once the limit changes to minus infinity to t, this is no longer relevant, and then this will just be minus infinity to t, and then we have V of t dt. So this is another expression via which you can use to find current. So now there are 2 or 3 different expressions we've talked about now that you can use to find the current flowing through an inductor. We said, first of all, I equal to lambda over L is one of the expressions you can use to find the current. Now we have I equal to 1 over L multiplied by integral of VT, V of T dt plus I of T naught. We have this, and then you have this for your voltage. So you can see now that we are collecting all the relevant information that we will need to carry out any kind of calculation that includes an inductor in the circuit. Okay, some other important things you should pay attention to here is that the current through an inductor is always continuous, so the current cannot be constant. If the current is constant, then there will not be a voltage across the inductor. If the current is constant, there will not be a voltage across the inductor. All right. So the current has to be changing continuously. This is very important. There has to be a continuous flow. And then an inductor behaves like a short circuit when current is constant. So when current is constant, this is just going to be a short circuit, right? So that means that whenever we are building our circuit, our understanding is that there has to be current flowing all the time. Otherwise, all you're just going to have here, current is constant, is a short circuit. So that means that current has to always be a function of time. Do you understand that? If it's not a function of time, that means it is a constant, all right? So if it is a constant, this is just going to be a short circuit. So it has to be a function of time, so that as time changes, the current is changing. As time changes, the current is changing. As time changes, the current is changing. Every second, every minute, the current is changing because of the change in time. So that is the only time this can remain an inductor. Otherwise, if you say current is just a constant like 2 or 3 or 4 or 5, just pick a constant, any current. This is just going to behave like a short circuit. So the only time there is a voltage across the inductor is when current is changing. So the IDT cannot be equal to 0. Pay attention to all of these important details. They will help us a lot in further calculations or further understanding. All right, let's take it a step further. We've said almost everything that should be said about a current in an inductor, but we should add more details. Let's see if we can crystallize and get more details about current in an inductor. V of T equal to L di dt. You know that already. This can be written in an inverse form, and that inverse form is what I just explained to you in the previous slide. When you just cross multiply, you make the I circuit of the formula, and then you integrate. So you have your I of T equal to 1 over L integral of V of T dt plus I naught. This I naught represent when our T equal 0, and it represents the current initially flowing in the inductor, like I mentioned earlier. So if you want to represent on a circuit, this inductor here is going to be like this. Like I told you, current always flows in from the positive end of the inductor. So you have current coming here. It's going to be I of T because it can be constant. And then you have V of T here, which is our source. All right. So if there's going to be a voltage across this inductor, this current here cannot be a constant. Once this current is a constant, there will not be a voltage across this inductor, and this is just going to behave like a short circuit. Just current going straight down this way. All right. So inductor power and energy, just like we found for the capacitor, we can find the power and energy in an inductor. Okay, so using the definition of power is always equal to voltage times current. So our voltage is L di dt, and then multiplied by current will give us Li di dt. So the power in an inductor will be giving us Li di dt. Okay, so and we know what our I is. Our I is 1 over L integral of T naught to T Vt V of T dt plus I of T naught. Okay, so you can just substitute the value of I into this, and then you have this entire expression here as a power. So, and by the way, this gives you, let me show you something. This is a formula here for P, as you can see, for power. This is one formula for power. Now this is a second formula for power. Okay, so this was derived from here, and then this was also derived from VI. So what you will see here is, here we said, okay, P power is equal to VI. Our V, we left I in the equation, and then our V is L di dt. We brought that in, so we got this expression for power here. In this case, we said power is equal to VI, so we left V alone here, and then we brought I in here. So you can see we have, in terms of you can use current to find power, and then you can use voltage to find power. Here is just voltage and the inductance to find power. Here it is current and inductance to find power. So depending on the kind of question or the kind of project or the kind of problems that you want to solve, you can use any of these two expressions to find the power. So here, if current is known, this is what you use. If voltage is known, this equation here is what you use to find the power. So how do you find the energy? All right, using the relationship of energy with power, you know that power is always equal to work done over time. So you have work done divided by change in time. So dW dt is our power, and if you're looking for work done, W, which is our energy, by the way, you have dW is equal to P dt. If you integrate both sides, you're left with work done will be equal to integral of P dt. Work done will be equal to integral of P dt. You know your P is Li di dt, so you can bring that in here. You have dW equal to Li di. If you integrate, you're left with 1 over 2 Li squared. This is what you're going to have at the end of the day. This integration assumes a reference of zero energy at zero current. So when there is zero current, there will be zero energy. Okay, so W will be equal to 1 over 2 Li squared. This is how to find the energy in energy in an inductor. This is how to find the power, and then we know how to find the current, we know how to find the voltage, and a couple of other important details. So let's take it a step further. Here there is a simple example here to just look at. So this is not a difficult one at all, but let's check it out. Derive an expression for energy stored in a linear inductor in terms of the flux linkage and the inductance L. You know what our energy is? We said our energy is equal to 1 over 2 Li squared. So, and we do know that our I is lambda over L, where lambda is the flux linkage and L is the inductance. And we were asked to derive an expression for energy stored in a linear inductor in terms of flux linkage. So you have lambda over L here. So eventually this gives you lambda squared over 2L. If you expand this bracket and carry out mathematical or simple arithmetic operations there, you obtain lambda squared over 2L. So this is pretty much straightforward. And you have a W equal to lambda squared over 2L. So energy now is in terms of the flux linkage, which is lambda here. All right. Second question, a 2 millihenry inductor has a voltage V equal to 2 cos 1000 T volt with I know the current initially flowing through the inductor as 1.5 amperes. Find the energy stored in the inductor at T equal to pi over 6 milliseconds. This is not going to be a big deal. We do know that our I equal to 1 over L integral of 0 to T V of T to T plus I of T naught. Okay, this I of T naught, we know it already to be 1.5. So we know our V to be 2 cos 1000 T. All right, and then we know our L also to be 2 millihenry. Automatically we can just substitute all of those, and we know our time is pi over 6, so we are going from 0 to pi over 6. So I will therefore be equal to 1 over L, that's 1 over 2 millihenry, integral of 0 to pi over 6 since our t is equal to pi over 6 milliseconds, and then our V as a function of time is 2 cos 1000 T dt plus I of T naught, would in this case will be 1.5. You can put 1.5 there. So if you carry out this integration, you have 1 over 2. 2 is a constant. So we have 1 over 2. If you integrate what we have here, you have 2 sine 1000 T divided by 1000 from 0 to pi over 6. Also, this is just basic and simple integration, so you can brush it up in case you are forgetting, and just remind yourself of how to integrate stuff like this, functions like this. So you have 0 to pi over 6 here plus 1.5. If you substitute 0 where you have T and pi over 6 where you have T and carry out simple arithmetic operations, what you are going to have left is 2 amperes, 2.024 amperes as the current flowing through the inductor. But what we're looking for is the energy. So our energy is 1 over 2. Half Li squared is our energy. Energy is equal to half Li squared. So 1 over 2, we have our L as 2 millihenry, that's 2 times 10 to the power minus 3, multiplied by our I, and then you square the I. Our I is 2.024, you put that squared and you carry out simple arithmetic operations, what you're going to obtain is 4.1 millijoules as the energy in the inductor. Okay, this is also an important example and it is easy to understand. All right, let's take it a step further. So the inductor phase shift between current and voltage waveform. So this is going to be the opposite of what happens, when we talk about a capacitor. You remember when we talked about a capacitor, we said current leads by 90 degrees and voltage lags by 90. In the case of an inductor, the voltage leads by 90 degrees and then the current lags by 90 degrees. So if you look at the curve we have here, this is the voltage curve, voltage waveform, the orange color, and then you can see the blue color is the current waveform, right? So you can see that the voltage is leading because we have the voltage first here, which is leading by 90 degrees, and then the current is lagging by 90 degrees. Okay, so if you compare this current with this voltage here, current is behind this voltage by 90 degrees, and voltage is ahead of this current by 90 degrees. And then that motion continues, that residual that concept continues throughout the waveform, no matter how long it is. Okay, so for capacitance, I remember for the capacitor, we said that the current is leading by 90, and then if you remember, then the current comes from somewhere right here and then goes down like this. For capacitor, goes down and then it goes up like that. Okay, so uh, pay attention to that.